Hello, in this video we're going to look at the Vec Operator, and what it does is it takes a matrix, so M by N, and transforms it into an M times N by 1 vector, and it's denoted by Vec of A. So the Vec Operator stacks the columns of A into a vector. So if this is our matrix A and these are columns of A, then what it does is one at a time it takes this, puts it in a vector, takes this column, puts it under it, and then it does it for every column of A and just stacks them on top of each other into an M by N vector. And now in some of the theorems and proofs and examples I'm doing, this is coming up. It's going to come up. Let me rephrase that. And I want to be able to point back to this. And plus, I just think property 5 is genius. Whoever thought of that is I'm just so impressed with. So here's a quick example. So let's let A be 1, 2, 3, 4, 5, 6, and then we take the Vec of A. So that says take this column, put it here. Take the next column, put it under it. Take this column, put it under it. And so boom, we get a vector. Now sometimes to save real estate, because these can get pretty long, you write them in a transform way. The transpose way, I mean. And so you take this and write it like this and put a tick. Either is okay, but sometimes, in my mind, this is the way I always visualize it. And for some reason, this is a little bit tougher, but it's easier to write when you're writing on pages. Okay, so in this video, we're going to use the Kronecker product, and I have a video out called the Kronecker product, and I'd recommend you watch it. So in this video, we're going to let capital letters be matrices, lowercase letters be vectors, Greek letters be scalars. And we'll just go through the properties. Some of these properties we won't prove because I think that you can do it on your own, and we'll keep the video at a good length. So the Vec of a vector is equal to the Vec of a, so this is a column vector and the Vec of a row vector. They're all the same, and it's just the column vector A. So property 2, the Vec of this vector multiplication is equal to B cross A, where this is the Kronecker product. So this says this is a vector, and take A times each of those components. And so what we want to do is show that. So here we have the Vec of A. Now let's write out what this is. So the first component times the first component, second component. Anyway, so this is the vector multiplication. But one note is that you see this, it's B1 in all this column, and then it's the vector A, and this is all B2, and then the vector A. So this can be rewritten as, now I'm keeping the Vec the same out front, so we're only going to deal with this. So the Vec comes down, and this first column can be thought of as B1 times the vector A, and that's then you get this back. And the same way, B2 times the vector A, all the way to BM. But when we take the Vec of this, it says stack those. So you take the first column and put it here, the second column, put it here, and so on to the last. But now if you think about this, so we have A all the way, but then we have the vector B1, B2, all the way to BM. But this is how we define the Kronecker product. You take A times each component of B, and that's what this is. So property 3, the Vec operator can be split by the addition, so the Vec of this matrix addition, so those matrix dimensions have to be the same, is the same as taking the Vecs independently and then adding them. The trace of this matrix product is the vector transpose times the vector. And actually, I think this one is pretty neat, that It's kind of amazing how it all works out. But let's prove that. So we have A transpose B, and when you do the matrix multiplication, this is what you get. So this is in a sense the first column times the first column of B. So remember, this transpose, like if you take the first column and then transpose it, then that first column becomes the first row. So you're taking that first row times the first column, which is this, which is essentially the first column here. Anyway, so you multiply this out. And now if we take the trace of this, we go this way. We have to add up those elements. So the trace of AB is actually this sum. So it's a double sum, Aij to Bij, and this piece here can be thought of as vector multiplication, which was what this is. So it's the jth column of A times the jth column of B. And then we're adding up each of those components, so you can think of it as this vector multiplication. So the vector, or the column 1, column 2, column M to column M. And well, this is the vec of A transpose. So remember how I said that it's sometimes that you write it in row form, and that's what this is. So this is a column. So if it were this way, it would just be the vec of A, but we transposed it. And then this is the vec of B. Well, that's what we wanted to show, that this trace is equal to this vector multiplication. So part 5, and actually this is the property that I think is just genius. So let's prove this. So the vector of ABC is equal to A prime cross A, so that's a Kronecker product, times the vec of B. And after the proof, I'll give you a quick little example of why this is so genius. Okay, so let's let A, B, C be matrices of size Mn, Np, Pq. And it's basically so we can do this multiplication. You know, the columns of this have to be the same as the row of this, and etc. So one note before we prove this is that the identity matrix can be written like this, and it's common notation that little ei means there's a 1 in the first spot and zeros elsewhere, and this says there's a 1 in the second spot of this vector and the zeros elsewhere. So this creates a diagonal matrix, the identity matrix. And then the matrix B can be thought of like this. So note that it's N by P. So there's P columns, and each one of these B vectors are dimension N. So if we take the matrix B and multiply it by the identity matrix, that's the same as B times the transposed identity, right? Because it's a diagonal matrix. But then this B can be thought of as, is written in these column form, and I, so these are row vectors now. So when you do this multiplication, you end up with this. So it's this first one times that, the second one times this, the P. And so you can really represent B times this sum, which is kind of cool in itself. So with this property, now let's start to prove this identity. So we have the vec of ABC, but let's rewrite B as this sum. So since A and C they're not indexed, we can bring them in and bring them out, and it doesn't change it. So we're going to rewrite it like this. But the Vec property, according to property 3, the Vec of this sum is actually the sum of the Vec. So that's property 3. Now in here, let's think about this as a vector. So, this is something by one vector. So this is a vector, and if we transpose this, it's a vector, right? So this is a It's a row vector, and this is a column vector. Now, by property 2, this can be thought of as the Kronecker product. The vec of this vector multiplication is the Kronecker product of the two. That's by property 2. Now, by a property of the Kronecker product, we can split those at like this. And so you'd have to go back and look at the Kronecker product video. So it can be written like this, and then since this isn't indexed, it can be brought out of this sum, but this vector, the Kronecker product, is actually the vec of the vector product. That's by property 2 of this video. And then the sum of the Vec operator is the vec of the sum, so we can take it back in. That's by property 3. And this right here we said was B initially, right? So this is B. And this is what we wanted to show initially, right? So we're done. Okay, so this is a cool property in itself, but how it's used to me is just genius. Okay, so here's a quick example of one use for this. So solving AXB. So A is a matrix, B is a vector, C is a vector in this case. This has been well researched. You know, if A is singular or non-singular, then there's different ways to solve for X. And so I'll be vague in that, but that's true. So now another system of equations is how do we solve for AXB? So these are all matrices, and C is a matrix in this case. And so my lowercase c and capital C look the same, but these are matrices. So how do we solve for X? So one approach is to use property 5 to transform it into this form, where these are vectors, and then solve it this way because it's been well researched. Okay, so what we do is we take the we take the Vec operator of both sides. So let's look at this. The Vec operator of this by property 5 is this. So we have a matrix times a vector equal to a vector. So that's exactly this situation. And we know how to solve for X in this situation. And so that's one approach to solve this crazy system of equations using something that's been well researched. Anyway, I just find that so fascinating. So let me get off the soapbox of it. So the next property, trace of ABCD, is equal to this. The vec of A times this Kronecker product times the vec of C. And this property can be used to sort of simplify this, the trace of ABC. But there's 4 here. But when you multiply it times the identity matrix, this is the same as this. But then with this, you can use this property. And that I can be any one of those, positions. So to prove this, the trace of ABCD can be thought of as the trace of A times this matrix. And then by property 4, it's a vec of this times the vec of this. But by property 5, we just showed the vec of these 3 matrices is this. And so we're finished. And so that's what we wanted to prove. Well, that's all I have for today. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.